Good morning, everyone. We are Team 18, and we are here to talk about our design, titration-assisted device for BVI STEM students. I'm Nama.
I'm Nee.
I'm Ifan.
So we started by studying the STEM workforce in the U.S., and we realized only 9.6 of the STEM workforce is made up of BVI students. And the reason is because there's an absence of assistive technology, which makes it difficult for blind and visually impaired students to learn simple fundamental aspects of STEM. For instance, with titration experiments, which is the focus of our design, we realized that without these cues, they cannot understand volume or color change. But with these cues, they're able to understand color and volume, which helps them understand the characteristics of various substances in titration. When looking at a solution for titration-assisted devices, we found that most of the existing solutions don't have the volume calculation or a titration-friendly setup. Our objective is to develop an assisted device that will enable students to perform titration experiments and increase their engagement in labs.
We constrained ourselves to a single experiment, sodium hydroxide with boric and boric acid, because of its safety. And we also constrained ourselves to the home science tool titration kit, and our user interface needs to be compatible with BVI individuals. Key requirements are the object detection needs to detect beakers at least 90% accuracy. Our volume calculation needs to have a less than 2% error while calculating volume to the nearest tenth. And our color tracking should be able to detect blue and purple at these HSV values. Our design solution is going to comprise a lab apparatus setup and the affordable mobile phone app that's based on a Python code. And the mobile app is going to be split into 3 different portions: object detection, volume calculation, and color tracking. Our design approach is to take the live titration video, detect the beaker, move on to detection of the initial volume added, output that initial volume, and go into a loop where we track the color of every single frame and output a frequency associated to the hue of that frame. Leave the loop once the experiment has been deemed complete by the program, and output the final volume and color. Object detection was based on an original model, YOLO V3 Tiny, which was trained using AlexNet because of its memory and power and its compatibility with iOS and Android. The algorithm will give the output label, confidence level, and the boundary box position, and send that over to the volume calculation algorithm, which will then crop the original frame to the beaker's boundary box, convert that frame into HSV, apply a mask and draw a boundary box around the liquid, and then use the boundary box as a cross section of a cylinder and use that to calculate volume, restore the image, and then create a region of interest, which the color tracking algorithm will then use to find the average hue of all the pixels within that region of interest, and through a frequency hue mapping, determine a respective sound based on the equation frequency is equal to 3 times the hue plus 250.
All right, so for verification, object detection was verified with a new set of figures, the example as shown below here. The AlexNet model was initially trained with 500 images for each instrument, while it was also tested with 100 plus new images for each instrument too. So as a result, our testing accuracy was 88.952%, which is slightly lower than the criteria of 90%. The verification of the volume measurement was performed by 2 methods. The one is using the app to detect the different volumes of liquid in the glass, and the other method is detecting the rectangular drawn on the paper, which represents the solution in the beaker. These 2 methods were iterated for 9 times respectively. So the maximum of our final result was 1.72%, which is definitely lower than the criteria of 2%.
For color detection, for color tracking, we ran the experiments with colors that we would find we ran the test with colors that we would find in our experiment, and we noticed that hues were in the expected range that we expected from the code. This is the frequency output that we received. The progression is in conjunction is accurate with the frequency mapping that we expected.
As conclusion, 3 algorithms have been successfully developed, and the usability and accuracy of this algorithm has been tested, and 2 of them fits requirements. For future work, we would like to train the model with more data set to improve the accuracy, and the following revisions you can see in here are also expected to be developed and improved. We would like to thank everyone who contributed to our projects here. Here's our reference.
My name is Nima Atiyama, and I'm a biomechanics and human performance concentration. Throughout my time here at Drexel, I have completed 2 co-ops at Terumo Medical Corporation. Through those co-ops, I learned about product development, test method development, formative usability studies, and design control documents. The most challenging problem I faced during my time in this project was creating the volume calculation algorithm. Firstly, because I had very little Python coding experience, and also because I needed to find the best way to detect the liquid in the beaker and then calculate the volume of the liquid in the beaker. To do this, I rewrote the lab protocol using the fact that the indicator changes from one color to another, in this case, blue to purple, to locate the liquid inside the beaker. I then modeled the liquid as a cylinder to find the volume of the liquid in the beaker. The algorithm works by taking a live video that has been cropped to the beaker frame from the object detection algorithm, and then ask the user to add indicator to solution. After the indicator has been added to the solution and the user has prompted the algorithm that the indicator has been added, the algorithm lets the user know that volume is being calculated. To calculate the volume, it detects the indicator by finding the blue pixels and drawing a boundary rectangle around them. It crops the boundary rectangle and determines the width and the height of the boundary rectangle in pixels and converts that to centimeters. It's able to convert the pixel dimensions to centimeters because it knows the inner diameter of the beaker being used for the experiment is going to be the width of the pixels. It finds the volume using the volume of a cylinder equation, which is pi d/2 squared times h, and lets the user know the volume of the liquid in the beaker to the nearest tenth. It does it to the nearest tenth because burettes in chemistry labs normally go to the nearest tenth when reading. The key accomplishments I was able to do during this project were define the design inputs and specifications for the project, researched existing solutions to determine shortcomings, which included trial runs of iLab and titration color-com, created and verified algorithm for volume calculation, drafted verification protocols, and drafted lab protocol to be used with the algorithm. Through this project, I have gained relevant skills like Python coding experience, research skills, especially with ASTM standards and IP, presentation skills, project monitoring and documentation skills, and teamwork skills. Thank you.
Hello, I'm Nama, and I'm a biomedical engineer. My concentration is biomaterials and tissue engineering. I was a co-op at Orbit Biomedical, where I was a research and development engineer. I assisted in developing a subretinal drug delivery device. I assisted the clinical trial team in developing a software for the clinical trial analysis, and I also assisted in protocol and verification, documentation, and testing. Some relevant skills I used in this project were presentation and public speaking skills, creating abstracts, scientific documentation, research and development, and Python language. My biggest challenge was finding the average use of real-time images with minimal error and with Python, just because at the time we started, I wasn't very familiar with it, and I was having trouble understanding how to calculate the color of an image. So to do that, I just had to study the syntax associated with color and with numerical analysis. I created simple algorithms to help me understand exactly what I was going to be doing. And I maximized my resources and I learned as much as I possibly could. And successfully at the end of the day, I was able to the trial and error, through working for months, I was able to get my code running effectively. So my key accomplishments were I also performed trial titration experiments in the lab for video analysis. I researched educational need of titrations, and I also created the code for color tracking and also the verification testing for that as well.
Hi, I'm Ifan. So my concentration is biomedical devices and imaging, and some educational experience that relate to this project will be the biomed 7-5 neural networks. It definitely gave me some insight into deep learning and helped me to build up a skill set of deep learning. The co-op I did at Epismart Nutrition and Avid Radiopharmaceutical definitely helped me to better teamwork with the members. Some key accomplishment in this project, I researched the existing solution and I compared the advantages and disadvantages of it. And I performed the pilot experiment to extract some preliminary data. In addition, I create and verify the algorithm for object detection, and I also drafted the algorithm for color checking. Further, I also collect 9,000 images for neural network training and fine-tune the AlexNet architecture to facilitate the identification of the lab instruments. So to me, the most challenging problem through the whole project will be collecting a large amount of imaging for a model training purpose. So in order to combat these issues, I self-taught myself to learn how to extract frames from videos. So eventually I successfully got these images, and that enables me to, enables the model to provide more accurate outputs. So thanks to the senior design project, the skills of the deep learning definitely got improved, and I practiced agile methodologies through the whole project. In addition, I feel like I'm more comfortable to quickly adapt to the emerging challenge now. And I learned how to build a very cool scientific posters, and I learned a lot about intellectual property protections. And then my skills of the team working definitely also got better improved.